All right, getting back into the lecture. We're going to talk about the derivative now of the logarithmic functions, And instead of writing out this proof on the board, I'm just going to walk you all through it on the slides. The first thing we're going to do is we're going to say, all right, well, if y is equal to the ln of x, then when we exponentiate both sides, e to the y is going to be equal to x. But that doesn't help us a whole hell of a lot, because now we're going to have an implicit derivative, right? And we're going to have to solve for dy dx. And that's what this does. So we're going to say, all right, cool. If that's the case, then the derivative with respect to x of this thing, that's going to be ey times y prime is equal to the derivative of this thing with respect to x. That's just going to be 1. So in other words, because d dx of e to the x is equal to e to the x, by implicit differentiation, we know d dy, or I might say d dx of e to the y is going to be equal to e to the y. Let me write this another way. It's going to be equal to d dy of e to the y times d dx of y, which is equal to e to the y times dy dx. Or we can write it as just y prime times e to the y, right? And that's what we're going to see going from this line to the next. And this is because of implicit differentiation, right? That's what we're doing here. So using that then, what we find is that d dx of e to the y equal to d dx of x is equal to e to the y times y primed equal to 1. Yeah? And that is y prime, not y to the first power. Okay, this is all well and good, but we've got to solve for dy dx here. So solving for dy dx, we get that dy dx is equal to 1 over e to the y. But up top, we said that e to the y is equal to x. So this is going to give us the derivative of the ln of x is equal to 1 over x. Everybody cool with this? So restating that, we get the derivative definition, number 1, but as a chain rule definition, it's just going to come out to be 1 over u du dx when you take the derivative of the ln of u. U is a function of x. So with this in mind, what's the derivative of the ln of 2x? Well, working this out, this is going to be 1 over 2x times the derivative of 2x, which is going to give us 1 over 2x times 2, or just 1 over x. And that's because of the second definition, the chain rule definition, right? So checking it out really quick, we're going to say that u is equal to the function 2x. So obviously then du dx is going to be 2. And by chain rule, we get that the derivative of the ln of 2x is equal to 1 over x. What's cool about this is going to be true for all of your first order polynomials. Or I mean for all of your multiples of x is what I should say. Not all of your first order polynomials, but all of your multiples of x. So if this was 3 instead, we'd still get 1 over x, right? But if we say 2x plus 1, it's no longer going to give us 1 over x. It's going to give us 2 over 2x plus 1. Make sense?
This is probably a dumb question, but where does the 1 half come from? Like,
The 2x here?
no, like when you're solving it, where does the 1 over 2x? Oh, that's 1 over 2x. That's fine.
Okay, well, I'm a sadist, so I'm going to give you a couple of these uglier problems. We're going to solve these. I'd like y'all to solve A. I'm going to do B and C on the board while y'all are solving A. I'll give y'all till about 15 after to get that done. So 5 minutes, give or take. So what do we think? Do we have A solved yet? Yeah? So what'd you get for A?
I got 4/x squared plus 2.
4/x² plus 2. Almost. Almost. For A, we're going to have d dx of the ln of 2x squared plus 4 is equal to, first you're going to have 1/u, right? So that's going to be 2x squared plus 4. 1/2x squared plus 4 times the derivative of 2x squared plus 4. And that's going to give us that is going to give us 1/2x squared plus 4 times the derivative of 2x squared plus 4 is going to be 4x, right? Times 4x. This is going to come out to be 4x over 2x squared plus 4. But we can factor out a 2 here. So factoring out that 2, we're going to get 2 times x squared plus 2 in the denominator. Dividing out, this is going to come out to be 2x over x squared plus 2. Make sense? So let's check the work really quick. Looking at that first problem, we have 1/u du dx, and we're defining u to be the function 2x squared plus 4. If that's the case, then du dx is 4x. And what we get from 1/u is going to be 1/2x squared plus 4. And what we get from du dx, well, like we said, that's 4x. And from here to here, we're just factoring out a 2 in the denominator and canceling it with the numerator. Now, looking at B, we have to use the product rule. Agreed? The product rule says if you have two functions multiplied together, the derivative is going to be the function u times the derivative of b plus the function b times the derivative of u. So that's what we have here. That's what's going on here. It's just the product rule. But the derivative of the ln of x, that's 1/x, and the derivative of x, that's 1. So we're going to get 1 plus the ln of x, which is exactly what we've got here. Agreed? Checking out the last problem, well, here we're going to use the quotient rule. So we have low d high minus high d low divided by the square of what's below. The derivative of the ln of x is 1/x, and the derivative of x is 1. So we're just going to be left up top with 1 minus the ln of x divided by x squared here, right? And that is in fact what we did. So jumping to another example, let's say we have the function, the ln of the square root of x plus 1. Well, here we can do some reduction really quickly. We can go ahead and rewrite this in terms of powers and take advantage of the properties of logarithms to pull that power out as a constant. When we do that, we get 1/2 times the ln of x plus 1. We're just taking advantage of that property, that third property of logarithm we talked about. Now we can take the derivative of this a lot more easily. Because the derivative of the inside, well, that's just 1. So we're going to have 1/2 times 1 over the inside times 1. To find that the derivative of our function is 1 over 2 times x plus 1. Now notice if we didn't take advantage of that logarithm property, we could still do this derivative. We would just have a really long chain rule. We'd have the ln, we'd have the square root, and then we'd have x plus 1. So we'd have 3 different functions here. Cool. So what about this? What are we going to do here? Well, the hint's in the title, right? We're going to rewrite this logarithm before we try to differentiate it. So how would we rewrite this? Folks at home, how would we start off by rewriting this? What properties are we going to use? Well, the first thing we have is 2 factors. We have the factor x, and we have the factor equal to the quantity x squared plus 1, that quantity squared, right? So we're going to take advantage of property 1 of logarithms. We're going to say, all right, cool, the ln of x times x squared plus 1, that quantity squared. This is equal to the ln of x plus the ln of the quantity x squared plus 1 squared. Then we're going to say, all right, well, from here, I can take advantage of the third property and bring down that power. So let's do that. Taking advantage of that third property, we're going to get the ln of x plus 2 times the ln of x squared plus 1. Now we can apply the derivative pretty quickly and easily to this. So apply that. Excuse me. We're going to have dx of the ln of x plus 2 times the ln of x squared plus 1. Well, this is equal to dx of the ln of x by the sum and difference rule plus 2 times by that constant multiple rule, right? 2 times the derivative of the ln of x squared plus 1. This thing is going to give us 1 over x. This thing's going to give us 2 times. Well, the derivative of the ln of x squared plus 1 is going to be a chain rule, right? So we're going to have 2 times 1 over x squared plus 1 times the derivative of x squared plus 1. And this is going to give us, rewriting this, 1 over x plus 2 times 1 over x squared plus 1 times the derivative of x squared plus 1 the derivative of this is going to be 1 over x plus 2 times 1 over x squared plus 1 times the derivative of x squared plus 1 is 2x. So we can rewrite all of this, right? We can rewrite all of this as 1 over x plus 4x divided by x squared plus 1. Notice we could have done this just by chain rule right here. We would have just had to have taken the derivative of this inside and multiplied it by 1 over all of that, right? When we do that, it'll end up reducing to the same thing we have on the board. So just to check our work really quick, the first thing we do is expand our logarithm. So from here to here is that first property. From here to here is that third property. Just bringing that power out. And then we differentiate it. And then we simplify to get exactly what we have on the board. Well, I don't know what that was supposed to be. 2. Okay. So we want to know some details about x squared divided by 2 minus the ln of x. So let me write this on the board since apparently I somehow managed to cut off this slide. So we've got the function f of x is equal to x squared over 2 minus the ln of x. What are some things we might want to know? Might want to know when this graph is flat, right? So when it has a derivative, when our function has a derivative of 0. So we can take the derivative, set it equal to 0, right? Doing that here, d dx of x squared over 2 minus the ln of x. Well, this is going to be x minus 1 over x. I would get that again. I just had to work with a similar function earlier today, except it was in complex values. Anyhow. So if we were to set this thing equal to 0, does that ever happen? Sure, only once though. F prime of x is equal to x minus 1 over x. Let's set that thing equal to 0. Well, when we add 1 over x to both sides, we get x is equal to 1 over x. So multiplying both sides by x, we get x squared is equal to 1. Now solving that, that's going to give us x is equal to plus or minus 1. Question: are we done? Not quite. Because if we look back at our original equation, x can't be negative 1. Since the ln of negative 1 does not exist, x is equal to 1. And checking out what they've got going on, they do the same thing, right? You might want to find the minimum or the maximum here. In this case, it's going to be a minimum. And we do that by finding the critical numbers. And we do that by setting the derivative equal to 0, right? So we take the derivative, and that comes out to be x minus 1 over x. We're going to set this thing equal to 0. And we get that x has to be equal to 1 over x. So x squared has to be equal to 1. So x has to be equal to plus or minus 1. But we can't put in -1 into our original function. So we have a relative min only when x is equal to 1.
So why can't you use -1?
That's because the domain of the logarithms, right? The domain of the ln of x is any number greater than 0. You can't put 0 or less through the natural logarithm, through any logarithm. So I'm going to keep jumping along here because I want to get into change of base and then into antiderivatives tonight. Let's say we have a of x, right? We're given some base and we're going to raise that base to a power. But we don't necessarily like that base. And we want to know, given another base, what power we would need to get the same number. So what I mean to say is, let's say, erase this. You're given this. But what you really want to know is this. So you know A, X, and Y, and you know B. What you're trying to answer now is what's Z. This is what the change of base allows you to do. So for example, log base 2 of 8 is equal to 3, right? And what we're saying here is that 2 to the third power is equal to 8. And for right now, we're just going to go through a couple of different details about logarithms and get back to this question, okay? So really quickly, just looking at a couple basic logarithms. Like I said, we know log base 2 of 8 has to be equal to 3 because what this is answering is what power you have to raise 2 to in order to get 8. Make sense what I mean? Now what log base 10 of 100 is asking is what power do you have to raise 10 to get to 100? What log base 3 of 81 is asking is what power do you have to raise 3 to in order to get 81? So looking at this, let's just jump straight to D. We're going to say that this is, for right now, equal to y. What this is telling us is that 3 raised to the y's power is equal to 81. Well, we happen to know some things about 81. 81 is equal to 9 times 9, right? We can rewrite 9 as 3 squared. So this is 3 squared times 3 squared. But this thing is just 3 to the 4th, because it's equal to 3 to the 2 plus 2, or 3 to the 4th. So y has to be equal to 4. In other words, log base 3 of 81 is equal to 4. Everybody cool with that? And checking our answer, hey, it is in fact 4. Okay, well, let's say now we're asked to solve log base 3 of 8. I don't like that problem. I would prefer log base 2, maybe. The change of base lets you address problems like that. It lets you say, I don't have a way of computing any one of these very easily. But if I change the logarithm, I could change, or if I change the base, I could get a nicer answer. I might still have a logarithm involved, but it'll be nicer to look at the very least. It'll be something I can understand more easily. That's what this idea of the change of base is going to do for us. So what the change of base formula is saying is that given log base a of x, this thing is going to be equal to the ln of x divided by the ln of a. Okay, whatever. What good does that do us? Well, that lets you say something like, once I get this erased, log base e to the 4th of 16. I have no clue what this is. And I'm being honest, I actually don't know what this is. But I do know that this is going to be equal to ln of 16 divided by the ln of e to the 4th. I know that this ln of e to the 4th is just equal to 4. So this is going to be the ln of 16 divided by 4. So not nice to work with, a little bit nicer to work with. Makes sense what I mean? Because what the hell even is e to the 4th? I know that it's a non-terminating decimal. That's about all I know. In fact, your computer won't calculate it because of what's called machine error. It has to cut off after like 16 digits. So your computer can't even accurately calculate what that is. But with the change of base, it can. So let's say we've got some of these other bases. First, what's C? Let's just jump right to that. What is the answer to C? Folks at home, what do y'all think? Are the folks at home with us still? What do y'all think C is? Is -1 in the domain of a logarithm? So this isn't going to exist. Not C. But the other two will. The other two are going to be the ln of 3 divided by the ln of 2 and the ln of 6 divided by the ln of 3. So checking the answers really quick. Log base 2 of 3 is going to be the ln of 3 divided by the ln of 2. These can be calculated. But this, I wouldn't want to deal with that, right? So the reason why this is useful, though, is because it lets us start differentiating things like some base A raised to a power. Because we can rewrite a to the x as e raised to the ln of a times x, right? Well, here, we're just going to get this constant, the ln of a, pulled out. So the derivative of a to the x is just going to be the ln of a times a to the x. It's kind of convenient. So looking at our derivatives in both the exponential and the logarithmic cases, given a base other than e, the derivative of a to the x is equal to the ln of a times a to the x. And the derivative of log base a of x is equal to 1 over the ln of a times 1 over x. So how the hell did they get this? We're going to prove 3 right now. With 3, we start off by saying, all right, I know that log base a of x is equal to the ln of x divided by the ln of a. So the derivative of log base a of x is equal to, by constant multiple rule, we can pull out that 1 over the ln of a times the derivative of the ln of x. So this is all going to come out to be 1 over the ln of a times 1 over x. So to get this, we have to use the change of base formula. And then our other two rules are the chain rules, right? Okay, so back to more radioactivity problems. Actually, let me use an example from life, directly from everybody's life. Let's say we have two different objects put in our hands. We know the weight of one, and we know the weight of the other one. We can't see these things, right? But whoever's watching us, they know the two different weights. And they put them in our hands, they're about the same size in volume, but not in weight. Say, all right, which one's heavier? The relationship between our ability to detect difference in weight is proportional to a constant. So what I mean to say is, I'm going to draw this as a picture so it'll be easy to see. I've got two different weights. This one weighs W. This one weighs W plus a little bit difference. Our ability to tell the difference in weight is proportional to how much that weight changed. So what I mean to say is delta W over W has to be equal to a particular constant. What this means is W and our ability to change or to experience the change in it is equal to a logarithm. Is everybody cool inside it? So W is going to be equal to, that's the log. So this is going to be E to KT, where T is the change, right? So we start off with weight 1 and we have weight 2. And this is telling us how much more the weight has to be in order for this other weight to be detected as different. Cool. So we've got weight 1 in hand. Weight 2 has to be at least this heavy or heavier in order for us to detect the difference in weight. If we wanted to know that rate of change, and we're told we don't know what E to the K is because it's already given to us as some other constant. I'm saying is E to the K is equal to A. So E to the K W1 is equal to A to W1. We're given this instead. We want to know how that changes with weight. That's the problem we're essentially solving up here, but with radioactivity. Does that make sense what I'm trying to say? So the derivative here would be let's say A is 14 for right now. Then the derivative of this would be equal to what? we gotta go back to these rules, right? It's going to be equal to the ln of 14 times 14 to the x. I use this example, and it's poorly rehearsed, admittedly, because something I want to point out here is that what we're talking about in this class with logarithms, exponentials, what we're talking about next with integration, antiderivatives, etc., have shown up in psychology. So even in subjects that we don't consider mathematically rigorous, like psychology, they have a lot of math hidden within them. In fact, this same experience just explains why it is, as you get older, time appears to move faster. Because this phenomenon doesn't occur just with weight, it occurs with anything with some sense of intensity attached to it, which personally is actually kind of cool, I think. But neither here nor there, I just wanted to kind of demonstrate one of the areas where this is going to show up or could show up in day-to-day life that we all experience. These equations describe our experience of time. As we get older, white time seems to shrink, like white time gets faster. It also describes our ability to detect weight, our ability to detect changes in light. It actually describes a lot with like interpersonal relationships as well. But getting to the problem on hand, we're going to take this derivative. What's going to happen here? What are we going to get in this particular problem if we take just the derivative of a here? Well, the derivative of 1/2 raised to the t over 500 of my mistake, 5,715. This is going to be equal to the ln of 1/2 times 1/2 raised to the t divided by 500 minus 5,715 times the derivative of t over 5,715. Got it right that time. And that just comes from this second rule, right? All we're doing here is applying chain rule. Nothing new, nothing fancy is happening here. So this then is going to evaluate out to be the ln of 1/2 times 1/2 raised to the t over 5,715 times 1 over 5,715, which we can rewrite as the ln of 1/2 over 5,715 times 1/2 raised to the t over 5,715. But we can rewrite this ln of 1/2, right? So let's go ahead and see what it rewrites as. Or can be rewritten as, I should say. The ln of 1/2 is equal to, by properties of the logarithm, the ln of 1 minus the ln of 2. So the ln of 1 is 0. So this is 0 minus the ln of 2, or just negative ln of 2. So we can rewrite our final answer as negative ln of 2 over 5,715 times 1/2 raised to the T over 5,715. And if we want to answer this final question, we would just plug in 10,000, right? Make sense? So checking out what we've got, they just leave the ln of 1/2 b. But it all comes out to be the exact same, right? Exactly what we've got written here. And then, like I said, to solve that last question, they just plug in 10,000. Which comes out to be a tiny decimal that I was not about to even pretend to know. For all intents and purposes, that's 0 to me. So what this is saying is after 10,000 years, the amount of carbon that you have isn't changing very much, not anymore, after 10,000 years. Having said that, I think we have hit a moment for a break. No, let's go ahead and charge. No, break. Let's take a break. Come back at 8:05.